You've heard that AI models learn from data, but how does a bunch of math actually learn anything? Today, we're covering the training process, how models go from random garbage to surprisingly capable systems. This is the core of machine learning, and understanding it will change how you think about AI. Training has one goal: find the weights that make good predictions. A model starts with random weights, it makes predictions that are essentially random guesses. Training is the process of systematically improving those weights. Think of it like tuning a radio. You start with static, then carefully adjust until you get a clear signal. Except instead of one dial, you have millions of weights to adjust, and instead of your ears, you have math to tell you if you're getting closer. The entire field of machine learning is essentially about finding efficient ways to tune these millions of dials. Let's break down how it works. First, we need a way to measure how wrong the model is. This is the loss function. For regression predicting numbers, we often use mean squared error. Take each prediction, subtract the actual value, square it, and average them all. Bigger errors get penalized more because of the squaring. For classification, predicting categories, we use cross-entropy loss. It measures how different the predicted probabilities are from the true labels. If you confidently predict wrong, the loss is huge. The loss function is your guide. It converts model performance into a single number. Lower is better. Training is essentially a game of minimizing this number across your entire dataset. How do we actually minimize the loss? Gradient descent. Imagine the loss function as a landscape of hills and valleys. The height is the loss value. We want to find the lowest valley. The gradient tells us the slope at our current position. It points uphill, so we step in the opposite direction downhill. Here's the process. Calculate the loss, compute the gradient to see which direction is downhill, take a small step in that direction, repeat. The step size is called the learning rate. Too big, you overshoot and bounce around. Too small, training takes forever. Finding the right learning rate is crucial. With millions of weights, we're navigating a million-dimensional landscape. We can't visualize it, but the math works the same. At each step, we figure out which direction reduces the loss and nudge all the weights slightly that way. Over thousands of steps, the model descends toward a valley where predictions are good. Backpropagation is how we efficiently calculate gradients for every weight in the network. Here's the challenge. The loss depends on the output layer, which depends on the previous layer, which depends on the layer before that, all the way back to the inputs. How do we know how much each weight contributed to the final error? Backpropagation uses the chain rule from calculus. It works backward through the network, calculating how much each weight affected the loss. Output layer first, then the layer before, and so on. This is why it's called backpropagation. We propagate error information backward through the network. The result is a gradient for every single weight, telling us exactly how to adjust it to reduce the loss. Without backpropagation, deep learning wouldn't be practical. It lets us train networks with millions of parameters. In practice, we don't train on one example at a time or the entire dataset at once. We use batches. A batch is a subset of your data, maybe 32 or 128 examples. We calculate the loss and gradients averaged over the batch, then update weights. This is called mini-batch gradient descent. Why batches? Using one example is noisy. Gradients bounce around too much. Using the whole dataset is slow. Batches balance noise and efficiency. An epoch is one complete pass through all your training data. Training typically runs for many epochs. You might see trained for 100 epochs with batch size 64. That means the model saw each training example 100 times, updating weights after every 64 examples. Here's the biggest pitfall in training: overfitting. A model can memorize the training data perfectly but fail on new data. It learned the noise, not the patterns. This is overfitting. Great training performance, terrible real-world performance. How do we detect it? We split our data into training and validation sets. Train on one, test on the other. If training loss keeps dropping but validation loss starts rising, you're overfitting. How do we prevent it? Several techniques. Dropout randomly disables neurons during training, forcing the network not to rely too heavily on any single feature. Regularization penalizes large weights. Early stopping halts training when validation performance stops improving. The goal isn't perfect training accuracy, it's good generalization to new data. Real world training involves a lot of practical decisions. Learning rate scheduling start with a higher rate, decrease over time. Data augmentation artificially expand training data by rotating images, adding noise. Transfer learning start with weights from a pre-trained model instead of random initialization. Modern frameworks like PyTorch and TensorFlow handle the math for you. You define the model architecture, choose a loss function and optimizer, and the framework computes gradients and updates weights automatically. Understanding what's happening under the hood helps you debug problems and make better choices. What you learned, loss functions measure how wrong predictions are. Gradient descent minimizes loss by following the slope downhill. Backpropagation efficiently calculates gradients. Batches and epochs structure the training process. Overfitting is the enemy. We want models that generalize. You now understand the foundations. Next, we'll move into LLMs, how these concepts scale to language models. Subscribe for more AI fundamentals. See you in the next one.